Very well. So, we will continue with this Laplace transform. We have already started the Laplace transform, and as a reminder, let's remember the concept of the Laplace transform. We already had a question regarding the Laplace transform in the second midterm, if you remember. The questions are with respect to the poles, which are the roots of the denominator in the system transfer function. The system function, for example, in one of the examples, was 1 over s plus a, as shown there. So it's a simple system. It's a first order system because the denominator has only one root, and that's why it is called this first order system. And that root is at s is equal to minus a. So depending on the value of that a, it may be a real value or a complex value. We locate a pole at the position of s is equal to minus a, which makes the denominator equal to 0. Okay? And then we put a cross over there. That will be our pole. That pole is a boundary. It must be a boundary. If it's not out of the region of convergence, it may be out of the region of convergence, then we don't care about that pole. But if it is related with the region of convergence, then it defines the boundary of the region of convergence. And the region of convergence is only with respect to the real part of the so-called S-plane, the Laplace plane, drawn like this. So this is an example plot of that transfer function. We have one pole at x is equal to minus a, and the region of convergence is bounded with that. If the signal, if the time domain signal is right-hand sided, if it extends towards right for positive t towards infinity, then so does the S-plane region of convergence. The region of convergence also extends to the right-hand side, therefore. And the situation is like this. Which means that it may have further consequences. One consequence is with respect to the inclusion of the j omega axis, or the real part of s, which is sigma, is equal to 0 axis, the vertical j omega axis. For certain purposes, we want this j omega axis to be included inside the region of convergence, because it indicates that when sigma is equal to 0, which means the Fourier transform, remember s is equal to sigma plus j omega, when sigma is equal to 0, s becomes j omega, and the Laplace transform becomes the Fourier transform. So if j omega axis is equal, then it means we have the Fourier transform. And once you have the Fourier transform, if it's a system transfer, for example, then it means the system is stable. If it's a signal, then it means the signal is a convergent signal whose Fourier transform exists. For that purpose, we will design, for example, our systems in such a way that we will try to locate the poles to eventually include the region of convergence. Inside the region of convergence, we want to include the j omega axis. Of course, we may have multiple poles. In fact, we did have multiple poles in the Fourier question in the second midterm. But nevertheless, it happens with the Laplace transform as well. Let's see an example. It's a second order system which induces automatically two exponentials. One of them is e to the minus 2t u of t, and the other one is minus 2e to the minus t u of t. Let's consider this signal as our time domain signal. What is the Laplace, sorry, it's not the Fourier transform, what's the Laplace transform of that? The Laplace transform is, from the linearity property, is a combination of the Laplace transforms of both of them, one by one. And they are individually first order systems, and the first Laplace transform is 3 over s plus 2 minus 2 over s plus 1. So this is the Laplace transform that we have. Very well. And as you see, we have two poles. You may want to compact this, okay, combine them, and make it a second order denominator or things like that. That's possible. But we don't really care about that for the time being. What I will emphasize is that automatically we have two poles. The first pole indicates a region of convergence for the first term, which is real part of S is greater than -2. That is a region of convergence. At S is equal to -2, there is a pole, and to the right of it, because that's a right-hand side signal, because we have a U of t, so to the right of the pole will mean real part of S is greater than -2. For the second term, we have real part of S greater than -1 this time. So somehow we need to combine these regions of convergences. We need to find the intersection of these two sets, in other words. Because both of them must be satisfied so that the combination region of convergence is satisfied. And the situation is, therefore, at -1 and at -2, we have two poles. One of them is to the right of -1, the other one is to the right of -2. So what is the intersection then? The intersection is towards the right of -1. Like this. By the way, do you understand why I'm drawing a dashed line crossing -1? Beg your pardon? Yes, that line boundary is not included in the region of convergence. It's strictly greater than -1. The real part of S is not greater than or equal to -1. It is greater than -1. So that is an indication. And as you see, this region of convergence, where horizontal is real, vertical is the imaginary axis, this is the S-plane, indicates the region of convergence. And this region of convergence does not include a pole. And that is a rule. If somehow you encounter a pole inside your region of convergence, that means you're doing something wrong. A region of convergence never includes a pole. So how many different regions of convergences, hypothetical regions of convergences, can we think of if you have these two poles? Which means how many different time signals these two poles may correspond to?
3.
It seems like 3. What are they? One of them is this one, to the right of -1. Tell me another one. To the left of -2. And then in between -2 and -1. That's also an intersection, because when you intersect right hand side and left hand side, a stripe is what you find. That is also a region of convergence. And interestingly, a non-existing solution also exists for this case, which is the intersection of to the right of -1 and to the left of -2, which is the empty set. The region of convergence could be an empty set as well. Isn't it? It's to the right of the intersection of to the right of -1 and to the left of -2 is an empty set. So we have in fact 4 possibilities. Is it a good exercise to think of the inverse Laplace transform of these? Let's write them. So what was it? 3 over x plus 2 minus 2 over s plus 1 may have several inverse Laplace transforms. One of them is this: 3e to the minus 2t u of t minus 2 e to the minus t u of t. And the region of convergence corresponding to this is real part of S is greater than -1. But we may have others. What are they? Let's make all of them left-hand sided versions. Then the signal also becomes negative. So minus 3 e to the minus 2t u of minus t plus 2 e to the minus t u of minus t if real part of s is less than minus 2. Now let's focus to these two cases because they are the most strikingly different ones. We have other tools. We're going to write them. They are just the combinations of this one and this one, this one and this one. Okay? We will come back to that. But what do they mean? First of all, the top signal over there is a negative exponential. So to the right hand side, when you extend it to the right hand side, this one and this one, the signals decay. They start at 0, so they have some certain values, and then they decay. The envelopes decay. They are very convergent signals. And that's why the real part of S greater than minus 1, which is this region of convergence, includes the j omega axis. So for the first one here, we have the region of convergence to include the j omega axis, which is the nice behaving signal or the nice behaving system. That's the good one. Can you see that these two signals are quite bad, quite wrong? What's wrong with them? They are decaying towards right hand side, but consequently they are increasing towards left hand side, diverging towards left hand side. E to the minus 2t and e to the minus t are growing for negative t. And because of these u of minus t's, they are very badly behaving to grow towards left hand side, from minus infinity to 0. So they are not good signals or systems. They are not behaving nicely. How come the Laplace transform still exists? Why? How can we say that a transform of this ill-behaving signal still exists under certain circumstances? Nope. As t goes to minus infinity, e to the minus 2t grows. It blows to infinity. The concept is multiplication of the signal. You have x of t, you remember that? And you multiply this with e to the minus st. Okay? And then integrate. That is the Laplace transform. Now, in this s, it's not only imaginary. So it's that e to the minus st thing has a real part and an imaginary part. If it only has an imaginary part, then it will have a magnitude of 1 only, and it will have no effect on this magnitude. However, we know that x of t e to the minus sigma t e to the minus j omega t dt is the correct expression, because S has sigma and j omega. And as you see here, so we have an integration. In this box term, we are multiplying our signal with something, with an exponential. The problem is, or the concept is as follows. If x of t is, let's assume that, increasing towards left hand side like this, like the signal that we have, it blows for negative t. That is x of t. Now let's try to multiply that with an increasing exponential in the same region. E to the minus sigma t, for what values of sigma does it become an increasing function? For negative sigmas. For example, sigma is equal to minus 2. If sigma is equal to minus 2, e to the minus sigma t will be e to the 2t. Let's make it even less than minus 2. Let's make it 2.2. It goes on like this. So this one is, let's assume, e to the minus 2t. And the red one here is, let's assume, e to the 2.2t. When you multiply them, what will be the multiplication? The multiplication will be e to the 0.2t, which is actually an increasing exponential. And because of that, since it's an increasing exponential, for the negative time indices, it means it's a decreasing exponential towards the left. And when you integrate that, no matter how slowly it may decrease, a decreasing exponential in the decreasing region is converged. It's a convergent signal. You can integrate it. You can find the integral under it. So you just multiply them. And this is the trick of the Laplace transform. It artificially induces another exponential such that if your signal is going unboundedly, by multiplying with that exponential, you're trying to bound it. You're trying to make it a convergent signal. The multiplication result, the box thing, is convergent. And you can only do it if you have some extra sigma. And as you see, this sigma here, sigma is equal to 2.2. Sorry, it's minus 2.2. Minus 2.2 is less than minus 2. So it is inside the region of convergence. Real part of s is less than minus 2. So you are multiplying with some suppressing exponentials. And the suppressing rate is determined by the sigmas within the region of convergence. By saying real part of s is less than minus 2, you see that I have to choose a suppressing exponential which makes sigma less than minus 2. It can be minus 3, for example. It can be minus 4. And that is why the Laplace transform converges. But since sigma is equal to minus 2.2 or minus 3, etc., is not including sigma is equal to 0, without proper choice of sigma, we cannot evaluate the Fourier transform. The j omega axis doesn't include the region of convergence, in other words. This situation could occur at the right hand side as well. So wherever that exponential is unbounded, you're just trying to suppress it. You're suppressing it from the right, you're suppressing it from the left. And then the integral will converge. As long as you can suppress. Now, let's think of the third possibility. And that possibility is to the right of minus 2 and to the left of minus 1. To the right of minus 2 means 3e to the minus 2t u of t plus 2e to the minus t u of minus t. And the region of convergence is as follows. Real part of s is greater than minus 2 and less than minus 1. Okay, so this is the region of convergence, and as you see, it's a stripe between minus 2 and minus 1. When you observe, let's bring it down a little bit, when you observe this signal, it's not a very good signal either, because this portion is still left-hand sided to the left, and it is growing to the left. E to the minus t is growing towards left. So how can we multiply both of the signals with such a signal, with such an exponential that the combination still converges? How does it happen? If we multiply, for example, with e to the minus 3t, sigma is equal to minus 3, which is e to the 3t. If you multiply both of them with e to the 3t. What's the multiplication? E to the minus 2t will have multiplied by e to the 3t, it will be e to the t. E to the t u of t and e to the 2t u of minus t. Let me open a parenthesis here. E to the, what was that? E to the t u of t plus or minus the coefficients, plus signs and minus signs, they are not important. E to the 2t u of minus t. So by this happens by multiplying with e to the 3t. By multiplying with that. Now, this one, by multiplying with e to the 3t, this portion, which was originally divergent towards left, now is now convergent towards left. Because e to the 2t is an increasing function towards right. So this one is limiting towards left, and therefore this thing is okay. It's a convergent signal. But look at that, e to the t, which is an increasing signal towards right hand side, and u of t is towards right hand side, unfortunately. Therefore, this coefficient didn't work. Now let's multiply the signal e to the minus 2t u of t, e to the minus t u of minus t with e to the t. Let's multiply, sorry, not e to the t, e to the minus t, which means sigma is equal to 1. Then, if we multiply it with e to the minus t, this one with e to the minus t, this will be e to the minus 3t u of t, and this one will be only u of t. Sorry, e to the minus 2t u of minus t, excuse me. This one will be better okay. It was still okay. This one is already okay, but it will be better okay. But this one, e to the minus 2t u of minus t, will grow even further towards the left hand side. So there is a problem with the choice of the necessary suppressing exponential. We have a problem. Can you propose a normal value of sigma by which I can multiply? Yes. It must be within the region of convergence. This parameter already defines where or what kind of a value you must select. As your friend has suggested, minus 1.5 is the best. It's a good choice. If s is equal to minus or sigma is equal to minus 1.5, e to the minus st, we are multiplying with that, which means we are multiplying by e to the 1.5t. Let's multiply these with e to the 1.5t. What will this be? E to the minus 2t times e to the 1.5t. It will be e to the minus 0.5t. Is that okay? So I'm going to multiply by e to the 1.5t, and the first term will be e to the minus 0.5t u of t. Now let's come back. This one, e to the 1.5t times e to the minus t, what will it be? E to the 0.5t. U of minus t. Now, do you agree that this new combination is good? Because this one is decaying to the right and it is to the right. Good. This one is increasing to the right, but U of minus t is to the left. So it is decaying to the left. This is also good. This is also good. So that's a good choice. As you see, the selection of sigma is equal to minus 3 didn't work. But the selection of sigma is equal to minus 1.5 worked. So I must choose the sigma to be in the region of convergence, so that the whole terms converge. If the j omega axis is included, then you can safely choose sigma is equal to 0. Then it will be the Fourier transform. The pathological situation is this one, minus 3e to the minus 2t u of minus t minus 2e to the minus t u of t. And the, region of convergence is empty set. This is the third one, the fourth one. What does it mean? Why is the region of convergence an empty set? I mean, what kind of a situation does it correspond to? Well, this one, the last one, is a both-sided signal, first of all. And you can never find an exponential towards the left or towards the right, such that while suppressing the increase, it not very much increases the suppressing part. Okay, you can never find a suitable exponential parameter. It doesn't exist. Just try it. Try to put some values of sigma and multiply it with this last fourth one and see whether you can find some reasonable sigma value which makes this thing integrable. And as a result, you will see that you will not be able to find anything suitable. You can try minus 1.5, minus 3, minus 10, plus 0.5, plus 2, plus 10. Just try, substitute these numbers, and you will see that it's problematic. Either of the signals, or both of them sometimes, will diverge. You will never find a both of them convergent integral situation. That will not be possible. So that's how the Laplace transform exists, even in places where the Fourier transform doesn't exist. The situation for Fourier transform doesn't exist means that such exponentials that you cannot use in the Fourier transform. You have to use e to the 0t, which is 1. So you don't try to suppress exponentials in the Fourier transform. But in Laplace transform, you are allowed to have an extra parameter, which is sigma, the real part. And you have to choose, of course, within the region of convergences. The right-hand side is 1. For the last one, you simply don't have it. One last remark before the break. When you compact this thing, it will become s minus 1 over s squared plus 3s plus 2. Okay? This is the simplified form. Which means that you have a zero of the system as well. At s is equal to minus 1. Which is the zero of the, or the root of the numerator. So maybe it is more accurate to draw it like this, to indicate it like this. And as you see, the existence of a zero inside the region of convergence is not a problem. Of course, inside the region of convergence, you may have zeros, but you may not have poles. It's not allowed. Now, what does a zero mean? I mean, physically, if it's a system at s is equal to 1, what's that? At s is equal to 1, it means sigma is equal to 1 and omega is equal to 0, by the way. Look at that. Omega is equal to 0, sigma is equal to 1. So it is e to the t signal. Okay. That signal is a node. It's a nodal point of the system. When you input that signal to the system, it doesn't output anything. It gives nothing. It is annihilating, vanishing at that signal point. S is equal to 1, or a 0 corresponds to that. For example, if it's a low pass filter, how can we construct or design a low pass filter, a nice low pass filter, in terms of putting or locating poles and zeros on the S-plane? We are going to see that. But of course, before that, we need to find some properties. We need to list some of the properties and solve further problems. But as I say, zeros are also important in terms of designing systems. In terms of stability and in terms of convergence, poles are the most important things because they indicate the region of convergence. We will continue with these topics. Let's give a 15 minutes break for the time being. After that, we will continue.